Sorry?
That's no, the speaker is not.
It's not working. Now it works. Yeah, okay. Okay, yes. Ladies and gentlemen, let's continue with the course Wind Energy Systems. And as you remember, so I hope you had an agreeable lunch, like I, and that our later start time helps to digest a bit. Okay, so we are still in this very complex and long chapter on the aerodynamics of wind turbines. It's normal that this chapter should be long because wind and turbines are aerodynamic devices, right? So we need to dig a bit into this. But I would like to start the next section actually with an overview of what we did already. Yeah? Maybe I should just tell you that at the very beginning, when we really started this course, we were first looking at some very crude numbers, like how much energy is in the wind, you remember that, and then how much energy could you extract by some blade that moves fast in a crosswind direction. Yeah? So these were the two things which were very crude, but which already gave the main topics of aerodynamics of wind turbines. And what we did then in this chapter, actually, in chapter 3, in which we are now, we first introduced this actuator disk theory. Actuator disk theory goes back to Betz. Yeah? In England, there was a person called Lancaster who also derived it earlier, but is for some reason not so often mentioned as Betz. This whole actuator disk model is just assuming that there is some force against the wind, and then you have this slowing down of the wind, and that already helped us to derive Betz limit and gets very important understanding of how the flow looks, right? It slows down through the wind turbine. Then we refined it a bit from actuation disk to rotor disk. Yeah? So now we assume that this disk is not just pushing against the wind, but we assume that the disk is somehow turned by the wind, and because it's turned by the wind, it will actually also impose a rotation on the wind. And that's why we have this wake rotation. And that is the thing that we treated in the last lecture. Yeah? So we had still not said anything about the blade. There was no lift coefficient, no drag coefficient, nothing about the blades was coming into play. We were just saying there is some disk that either pushes against the wind, or in the second thing, it pushes and rotates in the wind. But we didn't say anything about the mechanism, how the force is transmitted between the wind and the disk. And this is what we will do now. We will, so to say, go back to this lift and drag thinking of airfoils and bring it together with the momentum theory, which actually explained how the wind is influenced by the wind turbine. Yeah, so the problem of aerodynamics of wind turbines is, if you have an airplane that flies through the air with a certain velocity, and you know that the air is, for example, at rest, then you very exactly know the airspeed that the airplane will see. But in a wind turbine, you will actually, know that you influence the wind yourself, so the wind that you see is also influenced by the forces that you exert on the wind, unfortunately. And this is called induction, and that's creating all the problems, and that's why our approximations from the first lecture, of the very first lecture of this course, are not valid. Okay. So today we want to bring these crude approximations together, one based on momentum and the other based on lift and drag of an airfoil. Okay? So, blade element momentum theory is, I will call it section 3.4, blade element momentum, and that's abbreviated BEM theory. So it's when we say BEM, we always refer to what we will do in this chapter, in this section. Actually, this section will be long, will be today and tomorrow. So maybe I first recall what we did already on the momentum theory. So let's first recall what we know from the actuator disk. The actuator disk, I just said it in words, roughly speaking here, this was our idea, right? So here's the actuator disk. And so the first thing we did was actuator disk modeling. And what was behind was everything was just taking place in this axial direction, in the direction of the axis. That's why we call it axial momentum. So everything happened only in this direction. Axial momentum only, and nothing else. And so we could, with this, so the only assumption was that there is some disk and it exerts force, and with this we could already derive a few things, namely the Ct as a function of the induction. You remember maybe the formula. I think it's useful to remember it because we used it so often. We also derived the power coefficient, which was actually the thrust times the speed of the wind at this location, and that is actually this formula times 1 minus a again, for a, 1 minus a, and then to the power of 2. And we could also maximize this value with respect to a, and then you remember the optimal value of a was 1/3, the induction factor, and then we could derive Betz limit. So this was all based on axial momentum only. And what we did then in the last lecture, 2 weeks ago, was that we were refining this to the rotor disk. So it's not just an actuator disk that just pushes, but it's now a rotor disk, and the rotor disk is, of course, still the same picture. There is a wind turbine, but this wind turbine is now, maybe I draw it in 3D, it's now a rotating wind turbine, and it's pushed in this direction by the wind, and that means that the wind will be pushed in the other direction. So the wind is actually spiraling. Yeah, how do I draw it? Like this. Okay, so this is like how the wind moves after the wind turbine, because we get pushed in this direction. And by just comparing energy balances, we could also derive one thing. So there's, in addition to axial momentum, we also get also the tangential momentum. And the reasoning was very simple. I mean, if we want to get this disk turned, then there must be some change in momentum in the airflow, and this is what we assumed here. And if we look at the tangential velocity of the airflow, it will be different at different locations, radial locations. But we derived a formula, and I think, did I introduce the tangential induction factor already? A prime? Just, yeah, okay, great. So then we derived actually a formula that we bring everything together that we had, then we would just say it's actually A, the induction that we had, times 1 minus a, and then divided by some number, and this number I want to call lambda r, and lambda r is r times omega divided by u infinity. It's actually the local tip speed, or it's not the tip speed ratio, but it's a local speed ratio. Yeah, local speed ratio. How much faster do we move with our disk than the wind at a certain location?
Is it lambda squared?
Oh yes, thank you very much. Great. Wonderful. So this is what we derived, and only by looking at tangential momentum and the energy balance. So we assumed there was no energy lost. So maybe I should also say what was the velocity here that we called V3, the one that the air actually has, the rotational velocity, but as a velocity, not as a rotation velocity. Then this velocity will be actually this induction factor. V3 will be 2 times this induction factor times r times omega. So why 2? Because the assumption is, again, that there is no rotation motion here. There is like rotation motion at the disk plane, which is just described by the induction factor, and then behind it is like here, it's double. So again, at the actuator disk, we have the average of what is before and what is after. And so what I find important here is if you look at what this lambda r is, of course it's lambda, it's r squared. So this is proportional to 1 over r. So please keep in mind that, I mean, this is a proportionality sign, yeah? So it's not a letter. That the more you go to the inner parts of your blade, let's say here in the middle, yeah, there is more rotation in the middle than, I mean, it's not only a smaller radius, it's even moving faster. So it's significantly faster rotating in the middle. So the more you go to the inner parts of your blade, the faster it rotates. And also, what we should keep in mind is the faster we rotate, so the bigger this omega, so our wind turbine rotation speed, the lower actually this induction, the tangential induction. Yeah? So this is the tangential induction. So this is all already derived, and I don't want to derive it again, but maybe to remember this thing is basically the output of this the tangential momentum theory. And what we want to do now is BEM, blade element momentum theory. And what we will have there is we will we will regard again like we did in the rotor disk, we will regard an annulus of the air independent from each other annulus. Yeah? So that's the same as before. Regard annuli. So this is. So let me just plot the picture. So this would be one of these annuli. So here's the midpoint of the turbine. This is the radius of this annulus. This would be the thickness of the annulus, dr. And let me also plot maybe one blade inside. So here we have a blade. So what we will do is we regard annuli that are independent from each other. Which is, of course, a very strong assumption, right? I mean, before we assumed here an actuator disk, we assume the flow in the middle is completely independent from the flow outside, right? Everything here is at rest and is flowing with a free stream velocity, and then here it gets slowed down in the stream tube. That was our assumption here. Here already we made the assumption that each annulus is a different, rotating with a different speed. And they are completely independent, and this assumption we will also make now. So the annuli, the air that flows through this part of your wind turbine is, so to say, completely independent from the air that flows through this part of the wind turbine. And this air will be slowed down, and it will get some tangential velocity. But what is different now to the rotor disk is that we assume aerodynamic drag. So in addition, so this was like rotor disk. So it's the same reasoning. But in addition, we regard now aerodynamic lift and drag of our blade. So we look really at the blade again as if it were, I mean, now it's an airfoil and there is a number of these blades and so on. Regard aerodynamic lift and drag. But we assume two-dimensional airfoils. 2D airfoil. And so we will make the assumption, so to say, that each of these blade elements, that's a blade element, behaves completely independent to the others and has basically an aerodynamic lift and a drag that corresponds to its cross-sectional area, I mean the shape, and to the angle of attack, of course, that it has. So let's do a bit of notation. And one bit of notation I need is also the blade length here. I mean, you know how it's called. It's not the length, sorry. It's the direction in this is actually the chord, right? So chord C of R. And sometimes I leave away this dependency on R. Everything depends on R. Everything is regarding one annulus here. Then we might have more than one blade, right? So could be 3, for example. Yeah. So what we should also introduce is the number of blades. So this number of blades, and we will just call it B. For example, here we would have B equals 3 in this picture. Could be more blades or less blades. Maybe one thing that we should already introduce now, when we look here at this geometrical plot, do you remember how long this circle is? 2 pi r, exactly. And then you could actually define something that we will use sometime later, which is a very important quantity for wind turbines, and it is called the solidity. So the solidity is how much of the actuator disk is actually covered by blades. Yeah? And of course this will be different for every annulus. And if you think of this whole annulus length of 2r, and then there is a chord here and a chord here and another chord here, then you have 3 times the chord, or more general B times the chord, divided by 2 pi r, and then this is the fraction of this annulus which is actually covered by airfoils. Yeah? So we define something that is a quantity that's often used and which will appear later. That is the solidity. But it's at radius r, and we define it to be sigma r, and it is the number of blades times the chord length of the blades, that's like this, this and this, divided by the total length of this circle. So this is an important quantity. And another quantity that is actually this is solidity at a radius r. It's so to say the local solidity, but you could also look at the whole disk and refer what area of the disk is actually covered by blade, and then you would integrate, of course, over this area, and the overall solidity. Let me just define it also. We call it sigma. So sigma, what is it? It is the integral of all the chords, so it's B, assuming all blades are equal, right? So that's what we will always assume here. So B times the integral from 0 to big R of the chord times dr, that's the total area of the blades, right? Divided by the total area of the disk until, I should also define the total radius is big R as before. So we divide this by pi big R squared. So this would be the overall solidity of our actuation, our wind turbine. And very often these solidities are very low. It's a few percent of the total area. And that's, of course, the reason, I pointed it out before, why wind turbines are efficient is because the solidity is so low. because solidity basically, if you have a lot of solidity, if this is big, if it would be 100%, then you would need to have a lot of material for a given actuation disk area, and that would be a lot of material that you have to process and build and sell and install. I mean, turbines wouldn't look like the ones we have. But if you remember, there were actually turbines in the past, like 100 years ago in the US, 150 years ago even, that were used for pumping. Maybe you remember these very old pictures from Western films and so on. There were these wind turbines that looked like, I mean, this was the disk, and then there were actually a lot of blades, and basically one blade next to the other. Yeah, so they looked like this. Yeah? I will not draw it all. What was the solidity of such a disk?
100%.
100%, exactly, or 1. Yeah? So solidity is a number that you can conveniently express in percent. Okay, so what we want to do in blade element momentum theory is we want to regard now the blade element as a wing and look at local lift and drag coefficients, and then the problem is that if we want to compute the aerodynamic forces, we need to know not only the speed of our blade, but we need to also know exactly the induction of our wind due to our own wind turbine. So the wind will change its speed because we are there with our wind turbine, but our forces will depend on the wind speed. So there is some coupling, right? It's interdependent, and it will lead to implicit equations actually that are not so easy to resolve. But it's allowed and necessary actually to collect everything that we know about it. But I mean, the main difficulty, as I said, is now that we want to bring two worlds together, namely the world of an airfoil which just feels a force because there is wind, right? And the other thing is the wind that gets slowed down or changed because there is a force. And these two things together mean that there is a wind that depends on the airfoil, and the airfoil depends on the wind, and they couple with each other. And that's what makes blade element momentum theory interesting, but also complicated. So this was an example, sigma 100%. So let me draw this picture in a bit a more refined form and make the geometry of our wind, of our wing. And by the way, I should say that this is all extremely close to question 2 of the ongoing sheet. So what we discuss here is basically the concepts that we also want you to digest in the ongoing sheet. So the geometry and speeds of our blade. So maybe I draw this this blade a bit more in detail. Maybe I take one blade here. So that would be one of our blades. And this blade is, the wind comes from here. So there is some aerodynamic cross-section. This is our element. And this is what we call the blade element. And of course the area, what would be its area? It's, I call it DAB for area of the blade, right? We had that language before. The area of the blade is of course nothing else than the chord length times dr. Dr is this little distance here, right? And whenever something is infinitesimally small in this direction, I use just the usual d from, if we integrate over it, we get a real number. I mean, a number that's finite and not infinitely small anymore. Okay, so this is the blade element, and then let's look at what speed does this. I mean, the whole wind turbine will move. I mean, there is like, this is the hub, right? and there is a rotation speed, and the rotation speed is omega. I mean, we used that same omega before, so the rotation speed of our wind turbine is omega. So our blade element itself will move with a certain speed. Sorry for the noise. So it will move with a speed, and the speed will be r times omega, typically faster than the wind. Yeah? And then there is, in addition to this, there will be induced wind in this direction. Induced tangential wind. So what's the induced tangential wind? It's something because we get a force, I mean, we get pushed in this direction, so there will be a force on the air in that direction, so the air in the end must move in that direction, and in the disk of our rotor we will assume that this has the speed a prime times r times omega. So that's the induced tangential wind. That's, of course, comes on top of the motion because it's in the same direction. So this speed plus this speed together get the speed of wind that the blade feels in the rotor disk plane. Yeah. Then there's the other wind that comes from, maybe I should plot it somehow here. It comes from outside of the rotor disk, yeah. So that is like the real wind. It's not the real wind. It's the axial wind. I call it axial wind. And what would be the axial wind in the direction that flows through the plane using induction factors? It's u infinity. So our free stream velocity times 1 minus a. That was the definition of induction factor. And I don't specify what values a prime and a have now. I don't know it actually because it depends on how much force the blade will exert on the flow. But I know that there will be this induction. And so what I should mention here is that a is of course a function of r, and a prime is also a function of r. So they will be possibly very different at different locations. But I will not always put this r dependence into my formulas because it will be clumsy. Yeah? So they depend on the radial position, of course. So I think now we have all the speeds that are involved. The geometry is also hopefully clear. And now I want to look at what aerodynamic force will this little blade element feel. So in what direction will it get what force? That's what we want to investigate now. And for that I like to zoom in from, I assume that the blade is just at the top part, and then I look from the top on this blade. So I introduce what I call a top view. So blade element from top. And a blade should also be at the top. And it's of course for 1 r. So I assume that the r is now fixed. I mean, there is twist and so on in this blade, but I look just at this one element. And so here I would first draw a line that I call the, that's the, how do we call it? The rotor plane, or the rotor plane. That's the plane in which this blade element will move. The blade element, I mean, if you look at from top at this wind turbine, right? So then there will be a wing profile that could look like this. And this, as it looks okay, I think. So this wing profile will have some line which defines its geometric orientation. And this line is something that we can change with our pitch actuator if we want. But I will just assume it to be fixed. So we call this angle here beta. And what name did I want to give it? It's a set pitch angle. I mean, it's the pitch angle that we set. And the line with which we define this, actually this beta, this line, is, I mean, it's either the chord line or it's the zero lift line. And I think it's more convenient to take the zero lift line, but it must be something that your airfoil is well defined. So it's a geometric thing that for your airfoil is fixed. Do you know what is the zero lift line? Maybe I should say what it is. If you have an airfoil that flies, like in this direction, and you change the angle of attack, then you usually increase the lift first, if you make it bigger. So you get more lift. If you make it smaller, you get less lift. And if you make it so small that there is no lift anymore, then you have the zero lift line. And that, if it flies in this orientation, the aircraft feels no lift. I mean, it would, of course, then sink, but that's the zero lift line. So the zero lift line is actually the line, the orientation of the airfoil where this airfoil would not feel any lift. But if you increase it, and of course you increase it, then you will get lift.
If you put this airfoil this direction with the wind speed, it will feel no lift. Yeah.
Exactly. If the wind speed would be exactly in this direction, there would be no lift. Yeah. But of course there is now there is wind from this time, and maybe I should now draw this wind, the actual wind. So let me draw the two winds that we have here. So one wind is our axial wind in this direction. I draw it, it's actually the thing that I drew here, but I draw it now from top. So I have the axial wind. And I know already that it's u infinity times 1 minus a. And the other wind is actually in the rotor plane. It's this wind. And that is due to, on the one hand, I mean, the effective wind is what I'm interested in, because I'm now sitting on the rotor blade, right? So I see, on the one hand, I see this speed, my speed of motion, but then I also see, in addition, the induced tangential wind, because it's actually making the wind that I feel in this direction a bit stronger. So I call this the tangential effective wind. And what was it? It was R times omega. Without any correction, I mean, if there would be no tangential induction, then this would be already it. But because we have this extra induction, we get an 1 plus a prime. It's not minus, but plus, because it's... this is, yes, so that's a good point. So I'm now turning my blade in this direction. Yeah? The wind comes from here. And so the wind that I see comes from this direction. Yeah, I turn in this direction, but what I see comes in this direction. And the induced wind is also in this direction. It's actually like in this picture at the top also. So it's the same sense of rotation. Here the rotor disc was rotating in that area. But it's good to digest this. So the geometry we should really be sure about. And maybe I should just define one more angle, because now we have here another line, right? So this is now, whoop, if I take this whole line here, then I have another angle that is actually, maybe I make this long. So this whole angle here, is called phi. Let's just call it phi, and I call it the flow angle. It's actually the angle with which the flow, which the flow makes with the rotor plane. And then the remaining, this little thing here that remains is alpha, and that's the angle of attack of our airfoil. That will actually determine how strong the lift will be. So this is the geometric picture I wanted to share with you, and I would like to welcome questions regarding the geometry before we go on, because there were some.
One plus
Yes, that's a very important and good question, actually. So the interesting thing is, because we move in this direction, we get a force in this direction on our, I mean, that's at the end we will extract power, so we will get pushed in that direction. That means, on the other hand, we push the air in the other opposite direction. And the induction factor was, I mean, it's just a positive number. I mean, all numbers I write are positive here. I try to always keep the geometry, so to say, so that numbers are mostly positive. So this A prime is a positive number, the induction, and it goes in the opposite direction of our rotation. And together, this speed and the relative speed of my own motion together, they get summed up. And that's why I have a plus here. So without the induction, I would not just have the 1. And with the induction, I get this extra speed in the direction in which I anyway feel my wind already. So it's, so to say, making my wind a bit stronger, interestingly. Maybe just as a side remark, while everyone agrees basically on the speed in actual direction, that it's just the average between the front and the end, right? It's much less certain for the rotor disk theory, because at the beginning there is, so to say, no rotation, and then it immediately starts at the rotor disk, and then it remains there basically. So the detailed mechanism, there is no very strong physical reason why this should be the average of the front and the top, because I mean, it's so there is argument of how this A prime acts here in the rotor disk, because the rotor disk is now actually thick, and in reality it will get from no rotation to some rotation, and we know what rotation it will have at the end. We know that it had no rotation at the beginning, but this transition is so fast that we couldn't, I mean, it's a good approximation to say it's the average of the two, but it's not something that everyone would say is the best thing. But that's what is commonly done, and it is helping us in the analysis. So now we have, okay, the angle of attack is, I think, a bit misleading in this picture. I will just draw my picture a bit differently, because this line, I mean, just obfuscates that there is another line. So let me draw my airfoil like this, so that these two lines are a bit different.
So the angle of attack is the angle between our chord line?
Yes, it could be the chord line. That's, I mean, depending on how you define it, right? So usually, I mean, it's either with respect to chord line or with respect to zero lift line. I mean, there's possibly the chord line is not the zero lift line. For symmetric airfoil, the chord line is the zero lift line, but they are not symmetric, so there's a bit of difference.
So if it's not symmetric, it has to be zero lift line.
Yes, but actually, it's all. It doesn't matter so much. I mean, we just need to know which, and people either use that or that. Yeah? But it must be a line that's fixed to the airfoil. I mean, to the geometry of the airfoil. It's not something that varies if the wind is different or something. So it's some geometric one line which we define as the reference line. Yeah, I think depending. Let's just take chord line if you like. Okay, so now we have the geometry. And now everything that we still need is aerodynamic lift and drag, right? So these are the two things that we want to add, and they depend, of course, on the wind and so on. So let me first say, what is the effective wind? I mean, this wind here. The total wind here has a magnitude that I call big W. So the magnitude so this will be given by Pythagoras, right? So that's easy. We are just having an orthonormal system here, right? So we have the actual wind, which is basically the free stream wind velocities, squared 1 minus a squared. So this is the first part, and then the second part is this velocity. So I square all these things. It's r squared, omega squared, and 1 plus a prime squared. So now we have the effective wind velocity. That will be the velocity that our wing section or our blade element will see. And this velocity will determine how big the forces are. Yeah? And then I should draw maybe the same picture here, but I draw it new so that we have, maybe I first introduce, I have a CL that depends of course on alpha, and it's the 2D lift coefficient. And I will also have the CD, which depends on alpha, and that's the 2D drag coefficient. So these would be two numbers that are important. They will depend on this angle of attack. And how will they be leading to lift and drag? What I will draw now is actually the picture again, as I said. So I will have my airfoil here, maybe like this. Yeah. I have still my rotor plane here. But now I have my angle that I just defined before. I mean this, the effective wind angle, and here's my angle phi. And then I will have a lift which is in this direction, right? And I will have a drag in this direction. By the usual definitions of lift and drag, lift is always orthogonal to the wind and drag in the other direction. And because these is just a blade element, I will call them lift, not L, but I call it DL for the little infinitesimal lift. And this is DD. And maybe from the geometry we see something, if this phi would be 0, then the lift would be, of course, in the direction of the disk here. So the angle phi appears again here. Yeah, and if here's an, and also the angle phi appears here. Yes, I move it up. And I think I will clean the other blackboard. So this is just to get the geometry of the lift and drag forces right. So it's collecting everything we know about the geometry. So what we do at the moment is, let's say, it's not rocket science, but it's a careful collection of simple facts. But it's so many little facts that it gets complicated. So now I should add the formulas of lift and drag. So how do we get the magnitude of lift and the magnitude of drag? By the usual formula. So lift force, dl, is 1/2 times rho times w squared. That's like the dynamic pressure. You remember this expression always appears first. Then you need to multiply it with the blade area, AB. I said that before. What's the blade element area here? So now we have the area. Pressure times area is force, right? Pressure times infinitesimal area is infinitesimal force. And then this is multiplied with the lift coefficient. And the lift coefficient depends on alpha, of course. This is a very complicated dependence that we will discuss maybe a bit later. But I will drop it just for notational convenience. And the drag is the same, so we have the same dependence on the area and on the speed, but then it's multiplied with another coefficient, CD. And these lift and drag profiles, these lift and drag curves are something that are not of my interest here, but maybe it would be useful for a bit of knowledge for you to see how these things look like. So, I mean, CL could be, for a good angle of attack, something like 1, and CD for same angle of attack could be something like this. I don't know. This is some possible values, right? And of course, this would be already with a good angle of attack. And for different angles of attack, these curves will be different. So just to get you an example. So if you here plot alpha, and here you have CL of alpha, then depending if you have the zero lift line as reference, then this curve starts here at 0. If not, it will start at some other place. Typically, if it's the chord line, it will start here. And then the lift will grow, and at some point when you get too much angle of attack, you will actually stall, as it's called. And so this would be the lift curve. And the drag might be, this two-dimensional drag might be more or less constant or increasing a bit with lift. Actually here it would increase, I don't know, so something like this. This could, it's much smaller, of course, right? So this could be CD of alpha. So these would be curves, and they will be different for every profile, and I don't want to go into details here, but this can be looked up. Yeah? So for different profiles, you have lift and drag curves. So, but the magnitude is maybe important. 1 and maybe 1/20 could be typical magnitudes. So this was a little box just to get a bit of a feeling for CL and CD. But this is not our interest at the moment. So now we have a lift and the drag force, absolute values, and we know that their directions are not aligned with the axial and the tangential coordinate system, right? But they are in a different coordinate system, which is imposed by our effective wind. And so now we would need to compute the force that we get on our blade element due to lift and drag in the directions in which we move. That will be actually the one that will give us power, and in the direction in which we don't move, which will be actually the one that slows down the wind, right? So let me just add a few formulas here, but actually maybe the first thing I should add is, if we look at this, the sine of phi, the sine of phi is actually this wind divided by W, right? So just to get the collection, sine of phi is U infinity times 1 minus A divided by W, right? Just from this picture here. I mean, we have this axial wind and the total wind in this direction, and the sine of phi should be this ratio. And the cosine of phi is, on the other hand, the ratio of this top thing, right? R times omega times 1 plus A prime divided by W. So this would be the relations of the sine and the cosine. And I use that because I will need the sine and the cosine in a minute. So in this picture, the one that I just moved up, I would like to introduce now extra forces, namely the force in this direction and in this direction. So the force that acts on my airfoil. And I will call, of course, they are infinitesimal, and I call this the axial force, and this one is the tangential force. Axial and tangential. So I want to now get the total force on this airfoil element, on this blade element, but in this direction and in this direction. So I need to do a bit of cosines and sines in order to get these forces. And that's what I want to do now. And after we have collected these forces, we will make a short break. Okay, I think it's important to remain concentrated here. So, so the axial force. So what is the axial force? And maybe I do it first on the blade element. But actually, I will directly, because I will need that later, and I don't want to on all blade elements, on all B blade elements. Now, so because we have 3, we need to multiply it by 3 in order to get the total force in this annulus. So this is I call it dFA, and it will be given by B. B is the number of blades, and then for each blade we get this lift and the drag, and the lift will be multiplied with the cosine of phi, and the drag will be multiplied with the sine of phi, right? Because it's that direction, exactly. So we have here dl times the cosine of phi plus d drag times the sine of phi. And that's it already. I think this is exactly what I wanted. Of course, we can plug in these numbers if we want, but maybe it's not necessary. DAB was defined, so everything is defined and on the blackboard here. So the other force is the tangential force. And I should say that this tangential force is this dft, right? But please keep in mind, in reality, it's not just a force. In reality, it's actually, because it's an annulus, so this whole thing is a ring, right? The picture with the ring is already gone. But the tangential force is actually rotating the flow. Huh? I mean, it's of course, it's still a velocity and a force that I can interpret, but I could also translate it to a torque if I multiply this force with the radius. Yeah, then actually, in reality, it's a torque, so to say. Yeah? But I find it more convenient that it doesn't make anything more difficult if we work again here with forces, because at the end everything will be multiplied with a radius. We could call it a torque, and it will not add anything. So what is the tangential force? It's also, of course, depending on the number of blades. And then let's just look at it. I mean, it will be the lift multiplied with the sine in this direction, right? So dl times the sine of phi, and then the drag is multiplied with a cosine, but with a negative sign also, because it's not in the same direction, right? So here we have d drag times cosine of phi. And maybe now I want you to think a bit about the physics behind this whole thing, because my strategy is always to keep numbers positive if possible. So the sign should be with a positive sign here, right? Yes, good. Just to be checking that I have everything correct. So in the real wind turbine, I mean, this is now the force that the wing experiences. It's not the force that the wing exerts on the flow. I mean, that will be the opposite, of course. But the force in this direction, there will be a force. I mean, if I have my wind turbine, I have my blade, sorry, this is maybe the better blade. So the blade moves in this direction, gets wind, yeah? And it gets a force in this direction, and it gets a force in that direction, right? So actually both numbers we expect to be positive. So what, of course, this depends all on the angles and so on, but in a normally operating turbine, this number must be bigger than that one, right? So that we get pushed forward and not backward. Yeah? If we want to destroy energy, we would just have this negative. But if we produce energy, this will be a positive number. So let's just say positive if the blade element produces power. I mean, it doesn't consume. So again, we have nice positive quantities. And I give numbers to these formulas because we will need them we need to refer to them later. So I call this number 1 and this number 2. And maybe I keep this actually on the blackboard, but I also add this dAB equals C times dr, so that we keep that for later. And I remove this other blackboard. So please keep this picture, keep it in mind. But I have to remove it so that we have more space for writing. Okay, I suggest we meet at 35 past again. Okay, are you ready to continue, please? So we are in the middle of the journey to collect the equations that will describe the relation between the airfoil and the airflow. Yeah? And what we did already is we collected now the force that the air will impose on the wing. But now we know already that the wing will of course also have the opposite force on the airflow. And this is what will then be our balance equation, which will implicitly define the induction factors. So we have now these two formulas, actual force on the blade, on the whole blade element. Maybe I should collect it a bit. So maybe I draw this as a 3D image now. So I have the flow in this direction. Yeah, I have my annulus. Maybe I should draw this bigger here because it's on the front. My turbine rotates in this direction. And we, sorry? Was there a question? No. Okay. To close the door. Maybe it's too noisy. I close it. This one at least. And the rest, you want to keep it open, but maybe keep one or two open because I have a microphone and that helps. But just decide what you like. I think there was a disagreement here at the top. Yeah. Okay, but let's just discuss this a bit more. So what I just said is on this annulus, I mean on my, for example, 3 blades, so these could be my 3 blades, I collected already the total force that these 3 blades exert on actually experience, right? So this is dFA, is the force in this direction, dFA. And then the force in the actual direction is here, in the tangential direction is this one. And as I said, because it's actually in reality it's an annulus, I could also multiply this with the length of our radius if I like, and then I would get a torque. But this is not relevant because later on then the torque will change angular momentum, but I will just discuss in a minute why I chose to directly work with the tangential force. It saves me a bit of notation. And not much, but it's making the language cleaner. Then we have 2 forces with the same units and so on. So now the question is, so now we know that this annulus, I mean this whole annulus, there's air flowing through it. And this air on the 3 blades, or on the B blades, B, the number of blades, exerts a certain force in this direction and another force in this tangential direction. And then we know that because of conservation of momentum, the airflow must also get a change. So it must slow down due to this force. It must actually slow down. That's the actual induction that we had before due to this force. And it must also get this extra rotary motion in the other direction because it has this tangential force to produce. So this, let's start with the easier one. I mean, the slightly easier one is the axial induction. So let me just, so maybe first say axial and tangential force cause induction. And that means A and A prime. So these two numbers will be caused, so to say, by our forces. Cause induction due to momentum balance. And this is actually as before, right? So it's not something new. It's exactly the same formulas that we had before in the actuator disk and in the rotor disk. And so let's just think of what is the axial induction. So axial, we know that the force that we get, the axial force, of course in this case for this annulus, so that's why I put the D in front. What will it be? It will be the mass flow through this annulus times the change of speed that this mass experiences. Yeah? And we already derived before that the change of speed will be 2 times the induction. Yeah, so before there was no change, and afterwards there will be 2 times A, the change. So it's actually the mass flow, I call it dm dot. That's the mass flow through our disk. And then times 2 times A times u infinity. That's our change in velocity. Yeah, so that's the mass flow. And that's the change in velocity. It's nothing new. It's exactly what we had before. So I just want, yeah. So what is the mass flow? I should also specify dm dot is the mass flow through this annulus, and it's of course rho times the area 2 pi r times dr. And that's not it, right? So that's the mass, that's rho times the area. Now we need a speed to make it a mass flow. And the speed is u infinity, but not undisturbed. It's actually the speed with the induction factor, 1 minus A, the axial induction factor. So this is our mass flow. And it has a little d because of this little d. So we have now an expression for our axial force. And I call this actually equation, maybe I write it a bit more in detail. So we have dFA. So let's collect all these numbers. And in particular, yeah, I think we can collect things a bit easier. So we have 1/2 rho. So I put a 1/2 in front. That means I need a higher number later. And then I take my u. I have a u infinity. It appears twice. So I have u infinity squared. So now I have already the dynamic pressure. You remember this nice quantity that we can easier remember. Then I have 2 pi r times dr for the area. And then I need the factors. Now I have a 4 times A and then times in 1 minus A. I think now I've collected everything correctly, I hope. So this would be now my change in axial induction, in axial momentum. Yeah, so that's actually a force. So here's a pressure and here's an area, and these are dimensionless. So this is indeed a force. And that's actually the force from the perspective of the flow change. So, and this is what I call formula 3. And we immediately see that 3 and 1 together form, they are 2 different expressions for the same thing. So they must be equal, and that is actually one equation that will later implicitly define our induction factors. But now let's first collect the tangential force or momentum change. And for the tangential momentum, I think it's relatively easy to see that the mass flow is the same, but of course now it regards a change of velocity in the rotor disk tangential velocity. Actually, as we remember, because our disk is rotating like that, our flow will rotate in the opposite direction. But what will be the change in velocity of the flow? Maybe I first say it. So the tangential dft is dm dot. It's the same expression as before, but then times the change in velocity in the other direction, and that is 2 times a prime times r times omega. That is the velocity that the flow will have in this tangential direction after our disk. And I subtract from this 0. I mean, I can subtract 0 because at the beginning there is no rotation. This is actually the same reasoning that we did before in the rotor disk theory. So I could also make, I mean, this is a bit useless, so let me just not subtract it. The main point is it's also a positive number, right? So because this is positive, so it's really, the sign is correct. So I can also correct this or collect this in more quantities, and then I will get, again, this 1/2 I will add just for fun, so that will make this a 2, 1/2 rho, and then what we will get is u infinity, and then we will have here an r times omega, together that's also a velocity. Somewhere there will be the 4a prime here, right? From here, and from the 2. And 2 pi r is still missing. 2 pi r dr. And 1 minus a is also missing. Okay, maybe it's convenient or not. I mean, this is again a pressure, right? This is an area, and this is dimensionless. So from the dimension, I'm right. And I call this equation 4. So if I have now collected a lot of equations, that's it. And that's actually already the end, unfortunately. I mean, the end of our reasoning, because these equations I cannot easily resolve to get a and a prime. So if I fix everything else, so to say, the geometry, the speed of my blades, and so on, I could try to resolve them for axial induction and for radial induction. So it's actually 2 equations, right? So 1 and 3 and 2 and 4. Yeah, these are equations, 2 equations. For 2 unknowns, and our unknowns are a and a prime. And of course, this is an implicit equation. At every different radial position, it will be different. Yeah. And this can be, must actually be solved numerically. So I cannot just do it on the blackboard. And it's very complicated because everything depended on a and a prime at the beginning, right? So it's a very complex dependence on all these things. But just the number of equations matches the number of unknowns. Yeah? So we don't know how the flow will actually be influenced by the wind turbine. but we know two equations that describe it. And this you might find this a bit unsatisfactory, and I agree that this is, of course, much less agreeable than just deriving something like Betz limit and so on, where we could always say this is it, right? But that's the state of the art. So we have actually an equation that is left to be solved. And of course, the question is what you fix in this equation and what you assume to be unknown. And if you remember our geometry at the beginning, even the angle of attack and also therefore the lift and the drag coefficients, they would all depend on our A and A prime, right? So we would get a very, we would also need to include them. But what you can do to simplify your analysis is you just assume, and then you afterwards compute actually what will be your best angles. You assume that you will always operate or that you want to operate actually your wing with the right and the best angle of attack, where you get the specific fixed lift and fixed drag coefficient. And then you fix basically lift and drag coefficients. And with this assumed to be fixed, and then the angle beta actually chosen later, so that it will always lead to this angle of attack, you can resolve these equations a bit, not easier, you still need to resolve them, and then afterwards you can find out the angle beta that would be the right angle for your wind turbine. So that's a bit implicit, it's not 100% satisfying, but it's basically the equation where I wanted to arrive today. And instead of trying to resolve it, which I cannot anyway, I can just tell you a bit about how do people solve nonlinear equations, just so that you get a bit of a feeling of what happens there. I mean, what you have here is generally, if you have, so to say, some function f of some unknowns x, that should be equal to 0. That's basically what two equations in two unknowns mean. With some f, which is a function from Rn to the same space. Maybe here we have n equals 2. So it's a very simple thing, but generally we have such an implicit system of equations. And in order to solve it, there's many different methods, but they are nearly all variants of Newton's method. And maybe does anyone of you ever hear about Newton's method? Who has heard about Newton's method? Not so many. Okay, so then it's good. Then I say can be solved by, and it's a variant of it, so by Newton type methods, as we call them. And they are all based on actually iterative evaluations of your function. And if you have found the values of, in this case, a and a prime that make your equation 0, then you are happy. But usually you don't find them. And so what you will do is you will linearize this equation system by differentiating your function with respect to the unknowns. And then you end up with a linear system. So maybe I put this type in brackets, and I just tell you, no, I will not go into detail. It's useless. I mean, it could be a black box, and you could in MATLAB, for example, use fsolve, right? And fsolve is one method to solve nonlinear equations. The thing that I would like you to remember is we know how to solve linear equations, right? So linear equations, we just invert a matrix. And so everything here is based on iterative linear solves. Iterative linear system solving. Okay, and our main task from our perspective is not to write such a Newton type method for solving. That's something we can use, but our task as wind energy engineers would be to formulate the residual function big F. in a decent way, so that it depends on the things that we want to know, namely a and a prime. So this would be a long computer code for this function f, but once you have it, you can pass it to a root finder procedure like fsolve in MATLAB, and then you can go to a solution. And at the end, it doesn't feel so different from just evaluating an exponential or a sine function on a computer, right? It's just some root finding procedure. And I think it's an important task in engineering life to get a bit, to not get afraid from implicit equations, right? So it makes your life much easier if you just relax when you have an implicit equation and you just count, do I have as many equations as I have unknowns? And if yes, then you are okay. Okay. Okay, so I would suggest that we stop here and that we see and continue tomorrow with actually a continuation of how to go on here. Thank you.